let me say hi to everyone. Nice to see you again, and it's my great pleasure to present our today's speaker, Professor Dyakonov. He will speak about phenomenals in L1 geometry of the unit sphere. So please go ahead, Professor Dyakonov.
Thank you. So I'm honored to have this opportunity to speak at this well-established seminar. So many thanks to the organizers, Alexey and Vladislav, for their kind invitation. Okay, so you can see the title. Well, Fewnomial is a funny term, well, derived from few and polynomial. In Russian, it's малочлен. Well, let me first begin with this little piece of notation. So Pn will stand for the set of polynomials of degree at most n, just in one complex variable. Well, by a Fewnomial or Lacinar polynomial, one loosely, well, in Pn, one loosely means a polynomial that has gaps, meaning that it is somehow spanned by some selected monomials, z to the k, rather than by all of them. So it may have essentially, it's a polynomial that may have essentially fewer terms than the degree. Well, sometimes people insist that there be substantially fewer terms, and then something interesting happens. Well, in my case, I'll be interested with just an arbitrary set lambda of, say, non-negative integers. Well, a finite set of non-negative integers. So I write it as in this way. N, the capital N is the degree. Well, you take the interval from 0 to n in the integers, and you remove a certain fixed subset of positive integers, k1, etc., km, and you look at the space of polynomials, well, Fewnomials, if you like, of this form. Well, just linear combinations of the powers z to the k, where k runs through lambda with complex coefficients, and we denote it by p of lambda. Okay, so this is the main object to be studied, and my plan is to endow p of lambda with a suitable norm, actually the L1 norm on the unit circle, and study the unit ball, the geometry of the unit ball in the space that arises. So to be more precise, we shall restrict our polynomials to the unit circle, denoted by T, and view it as a subspace of L1 of the circle with the natural norm. So here the measure is just the normalized arc length measure on the circle. So this is the L1 norm, and we are regarding p of lambda as a subspace of L1. Okay, so p of lambda is this. It's the subspace of L1 formed by the functions with spectrum in lambda. Well, this the spectrum of a function in L1 is just the support of its Fourier transform. Well, the set of those integers k for which f hat of k, the kth Fourier coefficient of f is non-zero, and This is an equivalent definition of P of lambda as a subspace of L1. Well, in particular, let me observe that P of lambda is contained in H1, which stands for the classical Hardy space. So H1 is the set of functions with spectrum in Z plus, the non-negative integers, viewed also as a space of holomorphic functions on the disk, if you like. Now let me also introduce a couple of geometric concepts that will be relevant. Suppose X is just a generic Banach space. So this notation, ball of X, stands for the closed unit ball in X. Well, as usual, a point of the ball is said to be extreme for the ball if it is not an interior point of any line segment contained therein. Well, actually, instead of interior point, you may also say midpoint. So an extreme point is one that is not writable as the midpoint of any couple of distinct points belonging to the set. And also there is something called exposed point. So a point, say xi, of the ball is said to be exposed for it if this happens, if there exists a functional phi in the dual space x star of norm 1 such that this set over here, which is the intersection of the ball with the hyperplane phi of x equals 1. So if this set over here reduces to a single point xi, well, geometrically, you see, this means that xi is exposed if you can touch it with a hyperplane in such a way that the rest of the ball lies on one side of it, and the intersection reduces to xi alone. Well, it is easy to see that every exposed point is necessarily extreme, and every extreme point lies on the unit sphere, that is, has norm 1. This is easy. Well, the problem to be treated is this: characterize the extreme both types of points, the extreme and exposed points of the unit ball in P of lambda, our space of Fewnomials with spectrum in lambda, viewed as a subspace of L1. I'll tell you what the answer is, but first let me begin with a brief overview of what happens, well, in L1 itself to begin with, and in some of its subspaces, perhaps better understood than P of lambda. First of all, let me recall that the unit ball of L1 itself has no extreme points and hence no exposed points. Well, this is well known and easy to prove. Well, actually, this extends to generic L1 spaces corresponding to non-atomic measures. Well, in our case, I'm only considering the Lebesgue measure on the circle. So on the one hand, you have this, and on the other hand, if you move to H1, then the extreme points of the unit ball in H1 have been described, and these are known to be precisely the unit norm outer functions in H1. So this is an old result of de Loo and Rudin. Well, perhaps I should recall what an outer function is, and later on I'll have to mention inner functions. If you view H1 functions as holomorphic functions on the disk, as well as functions living almost everywhere on the circle, well, then an outer function is one that has no zeros. So a function, say f in H1 is outer by definition if it has no zeros on the disk, on the open disk, and if the harmonic function log mod f is the Poisson integral of a certain L1 function on the circle. Well, if you're not really familiar with this, never mind. There won't be much of that terminology. So anyhow, the extreme points of the unit ball in H1 are known. They have been determined, and there is a nice description, while the exposed points of the same unit ball are not so easily describable. In fact, this seems to be an interesting open problem, because those exposed points in H1 turn up in various connections, most notably in relation to the kernels of Toeplitz operators, and not only that. So there have been some activity in this direction, trying to understand what the exposed points in H1 look like. But there seems to be no nice characterization as of now. Well, lots of partial results have been collected, but no nice description. Well, let me also mention a certain extension of the Rudin-Deleuze result I mentioned previously. Well, an extension due to myself, which is relevant in this context. Suppose phi is an L-infinity function on the circle, and consider this kind of space. Well, this space K1 of phi defined in this way. So it's the set of those functions in H1 for which this other guy, the conjugate of z times phi times f, is in H1. You see the definition. And assume that this is non-trivial, which happens sometimes. In particular, well, if phi is just 0, the null function, then this reduces to the whole of H1. Or if phi is the complex conjugate of an inner function, well, an inner function is an H1 function, let's say, whose modulus equals 1 almost everywhere on the circle. So also in this case, the subspace in question is non-trivial. So in this case, you get something called model subspace in H1. Okay, so consider this this guy, and now the following turns out to be true. So this is something I proved quite a while ago. Well, in the last millennium, you see. This is a sort of generalization of the Rudin-Deleuze theorem on the extreme points in H1. So for a function f in K1 of phi, given a unit norm function in there, the following are equivalent. F is an extreme point of the unit ball if and only if this second condition holds, saying that the inner factors of f and the other guy are relatively prime. Well, this means that there is no non-constant inner function such that both f and its partner, well, this other guy, are divisible by that inner function in H1. Well, in particular, when phi is identically 0, this reduces to the Roux-en-Deleuze result. And another special case is this. Well, I'm getting closer to my current topic, which is, well, spaces of Lacinar polynomials or Fewnomials. But first, I'm going to tell you what happens in the non-Lacinar case, just for the space Pn, the full space of polynomials of degree not exceeding n. And here, well, you can deduce the result from deduce the characterization of the extreme points from theorem A up here. So in this special case, when phi is z bar to the n plus 1, you can easily check that the space in question reduces to P sub n, the space of polynomials. So recall, let me just for a moment, I'm going back to the definition of K1 of phi. Well, actually, this space K1 of phi is the kernel of the Toeplitz operator with symbol phi. For those of you who are familiar with Toeplitz operators, and most of you certainly are familiar with that. So this is actually the kernel of the Toeplitz operator with symbol phi on H1. And in particular, if this phi, the symbol, has this special form, if it's z bar to the n plus 1, then the space reduces to Pn, the space of polynomials of degree not exceeding n. And all we have to do is restate theorem A for this particular case. Well, if we write P for f, well, P for polynomial, and note that the role of the other guy goes to the polynomial P star, defined by this formula over here. Then that's it. Well, equivalently, the polynomial P star can be defined like this. Well, in terms of the coefficients, this is what the star operation does to the polynomial. It's a kind of involution on the space of polynomials. Okay, so along with your polynomial P, which you want to be extreme or non-extreme, whatever, in the unit ball, you consider this other guy P star, well, this reflected polynomial P star, and the preceding result gives you this. Well, given a unit norm polynomial P in Pn, the following are equivalent. So P is an extreme point of the unit ball. So as before, the space is endowed with the L1 norm on the circle. That is maintained once and for all. So for P to be an extreme point of the unit ball, the following condition should hold. The two guys, P and P star, should have no common zeros in the disk. So D stands for the unit disk. the open unit disk. Okay. And that's it. Well, of course, this last condition can be stated in terms of P alone. You may get rid of P star if you want. Well, basically, the zeros of P and P star are symmetric with respect to the circle. So basically, this condition 2b says that your polynomial P should have no pair of symmetric zeros with respect to the circle. Well, in saying so, I'm cheating a little bit because you should also interpret this condition appropriately for the pair of.
And having drew them together, we have extended the radial derivative of phi to the rest of.
I beg your pardon?
I'm sorry. I guess it's someone turned off his microphone, so no, it's okay. Sorry.
Okay, no problem. If you wish, you may restate this last condition describing the extreme points in terms of your polynomial P alone, and what it says is basically this. It says that P, on the one hand, P has no pair of symmetric zeros with respect to the circle, and secondly, this last condition holds. So at least one of the two coefficients, well, either the first or the last, well, the free term or the senior coefficient is non-zero. At least one of them. Well, this is how you describe the extreme points in Pn, which is the space of non-Lacinar polynomials. And also the exposed points in Pn have also been determined, and the characterization is this. Well, again, given a unit norm polynomial P in Pn, so the norm is always the L1 norm on the circle. So given a unit norm polynomial P in Pn, the following are equivalent. So for P to be an exposed point of the unit ball, the following, it is necessary and sufficient that the following be true. Condition 2b should be fulfilled. Well, the one that says basically that P has no pair of symmetric zeros with respect to the circle. Well, this condition 2b over here. First, that should be true, and secondly, P should have no multiple zeros on the circle. So the zeros of P lying on the circle, if any, should all be simple. Actually, well, this last condition is a refinement of what we had previously. Well, because you see, the zeros of P lying on the unit circle are also common. They are actually common zeros of P and P star. And if you have such a multiple zero, say a double zero on the circle, well, you can view it as a degenerate pair of symmetric zeros when the 2 points merge together. So this time, both true pairs of symmetric zeros and such degenerate pairs are forbidden. So recall that there should be fewer exposed points than extreme ones, and so the condition should be stronger, and so it is. Okay, now let's at last let's move to the case of lacunar polynomials or Fewnomials. Well, in doing so, there are certain new difficulties we have to face. And to mention one of them, we can no longer divide polynomials by their elementary factors. Well, so this is certainly a useful procedure when dealing with polynomials, but this time, well, if you do that, if you divide out a linear factor of the form z minus something, z minus a certain zero of your polynomial, the quotient will no longer be lacunary. Well, it need not be. As a stupid example, just look at this polynomial. So 1 minus z to the n is pretty lacunary. Well, it's a Fewnomial with only 2 non-zero coefficients, but once you divide it by one of its linear factors, namely by this one, by 1 minus z, you get something with lots of non-zero terms, which is not non-lacunar. Okay, so just to give you a flavor of the kind of difficulties that arise in this setting. Let's take a closer look at the lacunar case. So recall that we are dealing with a set lambda, which looks like this. So those k1, etc., km are the forbidden frequencies. And so P of lambda is certainly contained in P sub n, the full space of polynomials of degree at most n. And hence an immediate observation is that whenever a polynomial P belonging to the smaller space happens to be extreme for the bigger space, it will also be extreme for the smaller one. Well, this is just immediate from the definition. So, and for the bigger space, which is Pn, we know what the extreme points are. This means that the interesting case is that where the polynomial in question is non-extreme for the bigger space. And we know that the extreme points were described for the bigger space were described by condition 2b above, which says that roughly P should have no symmetric zeros, or more precisely, P and P star should have no common zeros in the disk. This time, the interesting case is that where condition 2b fails, so P and P star do have common zeros in the disk. Otherwise, your polynomial is even extreme for the bigger space and hence extreme for the smaller one. Great. So we may restrict our attention to that interesting case. So P and P star should have common zeros in the disk. And well, the answer to our question of how to recognize an extreme point will be stated in terms of a certain matrix cooked up from the polynomial. So let me proceed by describing how the matrix is cooked up. What kind of matrix I need? So recall that, well, our polynomial in question will be called P. It's a unit norm polynomial in P of lambda. So recall also that P star is its reflection. Well, this kind of reflected polynomial whose zeros are basically symmetric with respect to those of P. Okay, so now let A1, etc., AN be the distinct common zeros of P and P star lying in the disk, and let MJ be their respective, well, common, their common multiplicities for P and P star. Well, the minimum of the two multiplicities, you see. And let M, the lowercase m, stand for the sum of the MJs. Okay. Now, consider the polynomial G formed from those common zeros. So you see, the zeros of G are the AJs, well, those common zeros, and the symmetric points. Well, the zeros of the second factor are, well, the zero is 1 over AJ bar. So the zeros are the AJs and their reflections, the symmetric points, to the appropriate multiplicities. So this polynomial G is a common divisor of P and P star. And finally, consider the ratio P over G to be called R, which is also a polynomial of this degree. Okay, so we factor P, our polynomial P, as G, this G being built from the common zeros of P and P star. Well, G times the rest of it, which we call R. So R is this remaining factor. Great. Now, I have to construct a certain matrix from it. So consider the coefficients R hat of K, the coefficients of the polynomial R. Well, formally defined for all integer values of K, and let A of K and B of K be their real and imaginary parts, respectively, and further define these numbers A, well, A plus, B plus, and those minus numbers, A minus and B minus, well, lots of them, by these formulas. Okay, well, I'm not sure you're enjoying the formulas, but there are reasons for them being what they are. Okay, well, just in case. Okay, previously the polynomial R emerged, and now from its coefficients, I'm constructing okay, once A of K and B of K are defined like this. Well, these new numbers are defined, well, for these, well, these are the entries of the matrix to be dealt with, and they are defined for these values of J and L. And well, from these four matrices are built. So the matrix A plus is an M times M plus 1 matrix. Recall, well, the capital M is the number of forbidden frequencies for your Fewnomials, and the little m is the sum of the common multiplicities of those symmetric zeros. Okay, so we have four matrices, A plus, B plus, A minus, and B minus, whose entries are those numbers defined over here, up here, Well, in the case of the minus matrices A minus and B minus, well, the row index J runs from 1 to capital M as above, and the column index L runs from 1 to capital M rows and 2 little m plus 1 columns. Okay, well, I guess it's becoming tedious for you. Well, there are reasons for for the formulas to be what they are, as I said. But anyhow, this is a matrix constructed explicitly from the polynomial with bare hands. And finally, our main result number 1 now says, well, given a unit norm polynomial p in p of lambda, well, p is an extreme point of the unit ball if and only if the rank of the corresponding matrix Gothic M equals 2 times M, 2M. And that's it. So, not very simple, I'm afraid, but perfectly usable. Well, this Gothic M is a matrix constructed explicitly from the polynomial. So basically, what we did was first to divide your polynomial p by the common factor that it has with p star. Well, divide this bad block out, the block that makes it non-extreme for the bigger space, p sub n. We divide it out, and then we look at the coefficients of the remaining factor, of the quotient. And from those, we can construct our matrix. And so the answer is given in terms of the rank of the matrix that has emerged in this way. So that's it. And our main result number 2 describes the exposed points of the unit ball in similar terms. Well, not quite similar. There are certain essential complications to be dealt with. Well, let me describe the procedure, perhaps, well, briefly, without going into technical details. Well, recall once again that, so now I'm concerned with the exposed points. So again, the set lambda is something like this, and we are dealing with the space of Fewnomials, p of lambda, well, with the spectrum in lambda, and again, it is a subspace of p sub n, the full space of polynomials of degree at most n. And again, it follows that whenever a polynomial belonging to the smaller space is an exposed point for the bigger space, it will be exposed for the smaller one. This is immediate from the definition. So again, the interesting case is that where our polynomial is non-exposed for the bigger space. And we know when this happens because we had a characterization of the exposed points for that bigger space. And recall that the condition was that there should be neither degenerate nor non-degenerate pairs of common zeros for P and P prime. So the failure of that condition means that either P and P prime, P and P star have common zeros in the disk, or P has multiple zeros on the circle. Okay, so again, the plan is to cook up a certain matrix, this time M tilde, from the polynomial P, and the criterion for an exposed point will be stated in terms of that. Okay, so this time we also look at the zeros, say zeta 1, etc., zeta nu of the polynomial P lying on the unit circle, and well, let lambda 1, etc., be their respective . It is a simple zero, then its multiplicity is 1, and the corresponding mu j is 0. Otherwise, it's non-zero. So now mu will stand for the sum of the mu j's, and now we define the polynomial g naught built from those zeta j's. Well, the zeros of P on the circle to the corresponding multiplicities. So we have this this polynomial g naught that absorbs the zeros lying on the circle, and also the polynomial g defined as above from the pairs from those zeros that are symmetric with respect to the circle, and we form the new polynomial g tilde, which is the product of the two guys, g times g naught. This g tilde divides P, and the quotient P over g tilde will be called R tilde, which is again a polynomial. And now the matrix M tilde to be dealt with will be a certain block matrix built from the coefficients of R tilde in exactly the same way as M that appeared in the preceding theorem was built from those of R. The difference is that this time we take into account the zeros lying on the circle as well. Formally, you go back to the definition of M and you switch to the tilde notation. You put a tilde over each of the letters involved, and the formulas tell you what the matrix M tilde is. So the procedure is exactly the same. I'm not reproducing the formulas, which are rather tedious, perhaps. In this way, you construct a certain matrix M tilde, Gothic M tilde, with two capital M rows and two little m tilde plus 1 columns, and you consider the kernel of the corresponding linear map. Well, that matrix defines a linear map from R, Rn space of this dimension to m tilde plus 1 to the other one, which is R to the to capital M. Okay, and actually the criterion is stated in terms of the kernel or null space of that linear map. because, well, if you go back to the preceding theorem, well, there the criterion was stated in terms of the rank of the certain matrix. But we have the so-called rank nullity theorem from linear algebra, which allows you to restate conditions on the kernel, on the dimension of the kernel, as a condition on the rank of a matrix. So what the rank condition really said in the preceding theorem was that the kernel of the appropriate linear map has dimension 1 precisely. You can restate it in this way, and this time, well, in this way, the analogy between the two criteria will be more apparent, and the criterion will be stated in terms of the kernel of the matrix M tilde, actually. And to do that, just a little bit of terminology needs to be introduced. But that won't take long, I promise. So suppose you have a vector in the Euclidean space R 2D plus 1. It's an Rn space of an odd dimension. So suppose you have a vector in it, which we write in this way, a vector V, and then we say that V is a plus vector if this condition holds, if this condition over here is fulfilled. And finally, given a subspace V in R 2D plus 1, we define its plus dimension, well, denoted by dim plus of V, as the maximum number of linearly independent plus vectors in V. Well, if it were just vectors, then the maximum number of linearly independent vectors in it would be the usual dimension. This time we only consider plus vectors. The question is how many linearly independent plus vectors are there, and well, the maximum number is called dim plus, the plus dimension. Well, there are reasons for introduce this concept. Well, actually, well, basically the reason is that these plus vectors are essentially the coefficients of non-negative trigonometric polynomials. Well, a brief explanation is here. So an arbitrary real-valued trigonometric polynomial on the circle, so just a linear combination of a finite linear combination of powers z to the k, with k positive or negative. Such a guy can be written in this form. Well, it is the real part of a certain analytic polynomial of the appropriate degree, and it is parameterized by those real coefficients alpha k and beta k's. And so we may identify such a trigonometric polynomial, well, a real value trigonometric polynomial of degree at most d, with its coefficient vector consisting of those alphas and betas, okay, which lies in R 2D plus 1. And our plus vectors are actually those coefficient vectors that correspond to non-negative trigonometric polynomials. It's not so easy to understand which coefficient vectors, how to describe the coefficients of a non-negative trigonometric polynomial. Well, you can say that a certain matrix should be positive definite or something, but it's not really clear when that happens. But anyhow, this is what a plus vector really is, and so I have defined plus vectors and the plus dimension of a subspace of an odd dimensional Rn space, and with these definitions in mind, we can state the criterion for an exposed point. So given a unit norm polynomial p in P of lambda, it turns out that P is an exposed point of the unit ball if and only if the plus dimension of the kernel, so n tilde is the kernel or null space of the appropriate matrix M tilde built well from the zeros and coefficients of the polynomial as above, built in an explicit manner. And this is a reasonably explicit characterization of the exposed points. Well, maybe not awfully explicit. Well, because it's not immediately clear how to compute the plus dimension of a subspace. It may be, well, the plus dimension may be smaller than the true dimension, which happens sometimes. Okay, anyhow, we also have a sufficient condition stated in terms of the rank. So in analogy with theorem number 1, which described the extreme points, we have this kind of criterion. Well, a sufficient condition this time. If the rank of the corresponding matrix M tilde equals 2 times little m tilde, then M is an exposed point of the unit ball. And yet another sufficient condition for P to be exposed is easy to state. Well, it makes no recourse to the notion of plus dimension, so it looks nicer. Another sufficient condition for an exposed point. So if P is extreme point of the unit ball, and we know when that happens from theorem number 1, and if P has no multiple zeros on the circle, then it is also an exposed point. Okay, no more theorems. No, nothing. So here is the reference. The paper has actually been published already, or you may also consult the archive version. And let me conclude with a couple of open questions. So one is this: what happens in higher dimensions? Say on the D torus in place of just the circle, in which case you may also consider, well, you should consider a certain set lambda of multi-indices in ZD, a certain set of multi-indices, and you consider the set of Fewnomials spanned by those monomials Z to the alpha with alpha in lambda, where alpha is allowed to be one of those selected multi-indices, and you ask the same question: what are the extreme or exposed points of the unit ball in there with respect to the L1 norm again? It's not so obvious what the answer should be. And question number 2 is what about the Paley-Wiener type space? So what happens if we replace T, the circle, by the real line R? Well, in which case the Fourier coefficients get replaced by the Fourier transform, and you consider this Paley-Wiener type space, well, the set of those L1 functions whose spectrum, that is the support of f hat, the Fourier transform, is contained in lambda, where lambda is a given compact subset of R. And you ask the same questions. You seek to characterize the extreme or exposed points of the unit ball. Again, this seems to call for a new technique. Well, actually, in the non-lacunar case, I mean, when lambda is an interval, so this is a true Paley-Wiener space, the space of L1 functions with spectrum contained in an interval, in a given interval, then I know what happens, and there is a characterization of, I've done that. There is a reasonably nice characterization of both extreme and exposed points. Again, with a certain amusing complication in the case of exposed points. But otherwise, if lambda is a generic compact subset, say the union of two intervals to begin with, well, even in that case, I don't know what happens. Well, the linear algebra techniques no longer apply because it's no longer discrete. It's no longer finite. Okay, so these are some of the open questions that puzzle me, and that's all. So thank you.